I made a semicircle of wire out of a coat hanger. Let's find the y center of mass. It's a continuous mass distribution. We need to take each little mass and multiply by where it is in the y direction. This will be a dm. There'll be an infinite number of them along the entire wire. I don't care about the x position, I care about the y position. You have to imagine we'll multiply the dm times the distance to this axis, and we'll do that repeatedly and integrate those quantities. As we go across the entire semicircle, y is going to keep changing. dm is going to be a constant value if we increment by d theta, which would make sense if we're going to integrate from 0 degrees to 180 degrees. Well, r sine theta is going to be y, which we will put over here in the formula. I cannot integrate with respect to theta if my increment is dm. Maybe you see this coming. dm is equal to lambda times ds. ds is a small arc length found from r d theta. Now we can get rid of dm. This is dm. We can bring the constants out and integrate sine theta. That's negative cosine theta. And we'll go from 0 to 180 degrees. That'll take us from here all the way around to here. Plugging in 180 degrees, we get -1 for cosine 180, but there's a negative sign here, so that's a 1. Minus, putting a 0 in here, we get a 1. That's a -1. So we have a -1 here. So it's 1 minus a -1. Well, that's a 2. Now, what do you think lambda is? It's mass per length. Now we can see the masses have canceled. We're down to 2r squared over the length of the wire. What is that length? Well, 2 pi r is the circumference of a circle, so this is just pi r. One of the r's cancels, and we have 2 over pi r, which is good because we're down to something with just one dimension of length. Can you think and see if this is reasonable? Well, it's got to be more than halfway up. There's more mass above this point than there is below this point. Let's see if we can do an experiment and test this. We'll have to hang the wire from a couple of locations. Well, down the center makes sense. Well, we're going to have to hang it from another angle so we can see where the intersection lies. We have a diameter of about 41 centimeters. That means r is 20.5 centimeters, which is just what I get measuring it this way. Well, we know the center of mass is somewhere along this line. Now we have to find the center of mass by looking at the line hanging down from the pivot point. The center of mass will swing back and forth until it settles down underneath the pivot. So it's got to be at that intersection. So I'm measuring about 12.5 centimeters to the y center of mass along this line. That's my experimental y center of mass. Using the formula from the calculus, I get 13.1 centimeters for the theoretical. So now let's make sure we understand the orientation. We're talking about this being the y center of mass. Comparing the experimental to the theoretical, we have less than 5% error. How about the center of mass for a solid right cone? For starters, it'll be easier to see it if we flip it upside down and start here. Now you have to imagine there's going to be a bunch of dm's starting down here and moving all the way up. They're going to be at different values of y. We'll slice it up into a bunch of disks. Each disk will be a distance y from that point. Each disk will have a radius, lowercase r. So we want to integrate all of those dm's times their y as according to this formula. Do you think the dm is going to be constant? No. As we move up, the disks get larger. We have to figure out what dm is and then be able to come up with an increment that will match my y. How about we say that dy is the thickness of the disk? Now the increment matches the variable. Well, I think you know we're heading towards density. Linear, area, volume. It's got to be volume because this is taking up a volume. So we can say that the volume density is dm dv, a little mass over a little volume. So I'll say that the dm is equal to the density of this material times the little volume contained in that disk. Well, now, what do you think that volume is? Look at the shape of the disk. Can you picture this area of a circle times the thickness? That's the little volume.